Hey everybody, welcome to the 8A.7 video. This should technically say 8A.7 because it's still Unit 8A, not 8B yet. What we're trying to do in this video is talk about polynomial inequalities, and the reason it's in this is because we are dealing with polynomials, some of which are a higher degree than 2, but we're dealing with inequalities this time, not just equations. This is a good time to introduce you to this idea. So we want to be able to solve it analytically and graphically, and be able to represent the solution on a number line and in good old interval notation. So before we get to that, let's do a little bit of algebra review. Solve and graph. If I wanted to solve this linear inequality, I would just need to get the x alone. 3x is less than or equal to 7. Divide both sides by 3, so I get x is less than or equal to 7/3, which if I wanted to graph that, so this is solving it analytically. If I wanted to solve it graphically, what that would look like is if I made a number line. 7/3 is 2 1/3, so that would look about a little bit past 2. Because I have less than or equal to, you may recall that as a closed dot on the number line, and then we would shade the direction to represent where all the solutions are. Because it's less than or equal to that spot, I would shade all the way towards -infinity. So my answer in interval notation, also for extra practice, would be from -infinity to 2 with a bracket because the 2 is actually included. If I wanted to solve this equation, x squared plus 2x equals 3, because it's x squared, I'm thinking I have to factor, so I'd have to move the 3 over. And based on our previous videos, we could factor this to be 3 and 1, plus and minus. So my zeros were x equals 3 and x equals 1. For this section, other than zeros, I would also like you to think of these numbers as something called critical numbers. So write that a little bit more neatly. Critical numbers. And if I wanted to graph those critical numbers on a number line, I could come over here to -3 and put a closed dot because it's included, and I could go to 1 and put a closed dot. You can graph any equation you want on a number line, not just inequalities. And this is going to transition perfectly to the next example. Notice that I had an example of x squared plus 2x minus 3 equals 0. The next example is x squared plus 2x minus 3 is greater than 0. The only difference is that we're dealing with an inequality this time. So if I wanted to find my critical numbers, they would be the same as the previous example, because if I factored this, it would still be x plus 3, x minus 1. So my critical numbers are still -3 and 1. And for part 2, if I'm talking about a quote-unquote line test, that's really on a number line. And so just like the previous example, what I could do is make particular intervals. I could graph the critical numbers of -3 and 1. Because my inequality is just greater than, not greater than or equal to, both of these critical numbers would have an open dot on them, not a closed dot. And so what I've really created here is 3 possible intervals that we need to see if they're true or not. So one possible interval would be from -infinity to -3, not included. Another possible interval would be from -3 to 1, both not included because of the open dot. And the last possible interval would be from 1 to infinity. And what we're going to do is test each interval and see which one works in my factored form. And that should say greater than. And so below this number line, I'm going to show my work, and I'm going to make sure not to interrupt what I've already written up here at all. Let's say I want to test this first interval, anything from -infinity to -3. Let me pick a number that I know for sure is in this interval. So let's say I pick -4. What I want to do is plug -4 into this factored form to see if my answer over here is greater than 0. So if I pick -4, I would get -4 plus 3 and -4 minus 1. We're asking ourselves, is that greater than 0? Well, this would be -1 times -5, which would get me 5, and that is greater than 0. So this interval works. If I wanted to test something between -3 and 1, a good number would be 0 itself. If I plugged 0 in to this factored form, I would get 0 plus 3 and 0 minus 1. How does that relate to this 0 here? So I would get 3 times -1. So I get the answer of -3 is greater than 0. This is false, which means that this interval does not work. In my last interval from 1 to infinity, let me pick x equals 2. If I plug that into my factored form, I would get 2 plus 3, 2 minus 1. How does that relate to 0? I would get 5 times 1. 5 is bigger than 0, so this interval works as well. So if I actually wanted to write my solution or my answer, it's only the intervals that worked. So my answer in interval notation would be from -infinity to -3 union 1 to infinity. Notice when I did my work that I didn't write any of these numbers next to the number line at all. I feel like if you put these up here, it'll confuse yourself. So my suggestion will be to write your critical numbers first, write the possible interval second, then show your work like this down here. And as we keep going, I'm going to speed this up a little bit for those that might like a faster way. So this next example is not equal to 0 in any way, and it's x squared. So let's first move the 16 over and get x squared minus 6x minus 7 is less than 0. If, just like the last example, I continue to factor this, I'm going to get my critical numbers. 7 times 1 gets me 7, and -7 plus 1 gets me the -6, which means that my critical numbers are x is 7 and -1 from here. So if I wanted to solve this, I would graph my critical numbers first, 7 and -1. I know it's not perfect, but at least gives me a visual. So that means that I have 3 possible intervals that I have to check. Either this interval is from -infinity to -1. Now before we figure out the intervals, we need to figure out what kind of dot goes here. Because I have a less than symbol, just like the last example, I have open dots. So both of these must have parentheses on them. This interval would be from -1 to 7, both not included. And this last example will be 7 to infinity. And so after I have my critical numbers, after I figure out my possible intervals, I want to pick some answers and see if they work. So what I'd like you to do is pause. I would like you to try a number in each interval, just to make it more uniform. Let's try -2 in this interval, let's try 0 in this interval, and let's try 8 in this interval. So please pause, plug these numbers into this factored form, and see if you get true or false statements. So please pause now. All right, guys, so feel free to check my work. When I plugged -2 in for x, I got this first one not to work, so I crossed off that interval. The second interval, when I plugged in 0 for both factors, I got this to be true. I got -7 is less than 0. And the third example, I got 9 is less than 0, which doesn't make sense. So I said that this interval does not work. So my actual answer is just the interval from -1 to 7. So that would be my boxed answer. This next example looks like we have a degree higher than 2. So the first thing I would check for is if we can factor by grouping. It looks like we can. So what I'd like you to do is pause, factor by grouping, see if you can find your critical numbers. So please pause now. So when I factored by grouping, I got x squared minus 4 and x plus 2 is less than or equal to 0. When I came over here to find my critical numbers, if I solved this first one, I got plus or minus 2 as my zeros or criticals, and I got -2 again, which means my critical numbers are just 2 and -2. And so that's why I graphed them on my number line. Because my inequality is less than or equal to, this time -2 and +2 are included, so I'm going to put closed dots on those. And again, I have 3 possible intervals for this one. So either -infinity to -2 included, -2 to 2 with the brackets, or from -2 to infinity, included, not included. Now, if you're interested, a quicker way to check this would just be thinking about positives or negatives. So again, if we wanted to pick something in this interval, like -3, 0 is my favorite for this interval, and 3. You can think about if your number is going to be positive or negative rather than plugging in each one. So if I took -3 and plugged it into this form here, -3 in here would be 9 minus 4, so this would be a positive answer. And then if I put -3 in here, that would be a negative answer. So this would be a negative, and a negative has to be less than 0, so this interval works. If I plug 0 in here, that would be 0 squared minus 4, so I'd have a negative answer. If I plug 0 in here, 0 plus 2, I'd have a positive answer. Negative times positive is a negative. A negative is less than 0, so this interval works. If I plug 3 in here, that would be 3 squared minus 4. That would get me a positive answer. 3 in here also gives me a positive answer. Positive times positive is a positive. Is a positive less than or equal to 0? No. So this time, two intervals that are next to each other worked. So if I think about how to write my final answer for this one, I wouldn't write two separate intervals because this is continuous. So this interval will be all the way from -infinity all the way up to 2. So the best answer would be -infinity to +2, done. So it is good to think about the signs. Now, if this method that I just did here didn't make sense to you, feel free to actually plug in the answers like I did back here. You could show the work for each one. If you like this more, feel free to do it. I want to show both ways. Last example here, we have x to the 4th, a higher degree polynomial. Let's see if we can solve it in a similar way that we have been doing. If I move the 27 over, I'd be greater than or equal to 0. Let's see if I can factor this. X squared times x squared is x to the 4th. 9 times 3 is 27. And -9 and -3, would be a -12. So this did factor. Awesome. So if I wanted to find my critical numbers, I would set x squared minus 9 equal to 0. And I would get two answers of plus or minus 3. And if I set x squared minus 3 equal to 0, I would get two answers. X would be plus or minus √3. So on this number line, I would have 4 critical numbers, not just 2. And so √3 is about 1.7-ish. So my roots would look like this, or my critical numbers. I might have -3, -√3, +√3, and +3. So I'd have multiple intervals to check this time. So because I have a greater than or equal to, all of these possibilities are included, so I'd have a closed dot on all of them. Rather than squishing in the interval notation, I will just do that later for the sake of time here. So let me think about what numbers I would pick in each interval. A number that's less than -3 would be -4. A number that's between -3 and -1.7 is -2. A number that's between -√3 and positive would be 0. Between 1.7 and 3 would be 2, and then a number bigger is 4. So if I think about my signs here, if I plug all of these into this boxed green answer, -4 squared is 16. 16 minus 9 is a positive. -4 into this would also be positive. So positive times positive is positive. Positive has to be bigger than 0, so this interval works. If I plug -2 in, that would be 4 minus 9, so I get a negative, and this would be a positive. Negative times positive is a negative. A negative cannot be bigger than 0, so that's out. This interval, if I plug 0 into both cases, I get negative times negative, which is a positive, which is bigger than 0. And if I kept going on the next interval, if I plug 2 into both, I got that this does not work. If I plug 4 into both, I would get 16 minus 9, which is a positive, and I would get 16 minus 3, which is a positive, so I got this interval to work as well. Which means that my final answer in interval notation would be this first interval, -infinity to -3 bracket, union, this interval, -√3 to +√3, both brackets, union, this last interval, 3 to infinity.